And where we're going is actually in this book back a chapter. So we're going back now to chapter 13, which is carbohydrates. So these last few chapters, carbohydrates, lipids, and proteins, I believe. Obviously, like I mentioned before, we're not going to cover everything that's in the chapter. So you are responsible for whatever we sort of cover here in class. And if I happen to post maybe a recorded lecture or whatever's in that recorded lecture, but pretty much whatever's contained within either live lecturing this week or recorded lecturing is what you're responsible for. And again, it's probably not going to be every single thing that's in these last few chapters and stuff like that. So we're going to kind of hit some of the high points here as we go through these last few chapters here this week. All right, so like I said, we'll finish up the organic part during discussion this week, the two nitrogen containing groups, but here we will, I stopped hitting the wrong button there. There we go. We'll start off here with our carbohydrates. So carbohydrates, breads and stuff like that are sometimes referred to as sugars. Let's talk a little bit about chiral molecules, which is a big sort of part of carbohydrates and so forth. So a chiral molecule basically means that we have, when we look a lot of times, especially in carbohydrates, we look at what is sometimes referred to as the chiral carbon. Carbohydrates pretty much are made up of carbons, hydrogens, and oxygens. So a lot of times there's carbon involved. And a lot of times we look at this carbon and we basically look for that carbon, and if it has basically 4 different groups attached. So they have the same number of atoms, but they're arranged differently in 3-dimensional space. But, you know, when we look at sort of carbohydrates, we look at the carbon and we look for kind of 4 different groups attached to it. And that would make what is referred to as a chiral carbon. And basically what that means is if you sort of, as we will see here, and why there's the hands sort of in the pictures here, basically what that means is if you take a chiral sort of molecule, I'll just draw an X, and you put it up against a mirror, and you take the mirror image and you pull it out. The mirror image is non-superimposable. So the mirror image of a chiral molecule is non-superimposable on the original sort of image. And that's basically what the hands are there in the picture. So if you put your hand up to the mirror, what you get staring back at you basically is your other hand. And if you take your hand out of the mirror, no matter what you do to that mirror image, you could rotate it all the way you want, you'll never get it to fit perfectly on top of the original image. And it may appear that it does, but again, if you pull out the mirror image and if you rotate or even flip it over, although they're both palms down, your thumbs are on different ends. If you get the thumbs together, one's palm up, one's palm down, so they're not in the same orientation. So you could rotate your hands as much as you like. You'll never get those guys to perfectly basically superimpose on one another. And that's basically because there's kind of 4 different groups attached. So there's always going to be sort of a group that's off when you take the mirror image out as it reflects in the mirror. There's always going to be some type of group that will be off. There'll be a different sort of connection that sometimes happens as well. And that will cause, like I said, that mirror image really not to be superimposable. To look at that, if we look at our mirror images, chiral molecules cannot be superimposed on their mirror image. So if we look at this guy on the bottom here, this would be the black circle here is a carbon. And it basically has 1, 2, 3, 4 different groups attached to it. So when you put it up in front of a mirror, the hydrogen reflects there, chlorine comes front, the iodine comes here, and the bromine, as you can see, reflects all the way to the back. Again, if you pull out this mirror image out of the mirror, like they do over here, you can see that even with kind of sufficient rotating, as many times as you're going to want to rotate it. There's always going to be a problem here. And we can see the problem is actually with these two guys in this particular example. The chlorine and the bromines really never line up correctly. And that would be, again, what is referred to as a chiral molecule, mirror images that do not superimpose on one another are chiral molecules. Now, mirror images that actually do superimpose, so it is possible to get some mirror images that will actually superimpose on each other. Those are what are referred to as being achiral compounds. And achiral compounds are compounds where basically with sufficient rotation, you can pull out this mirror image like we have here and do some sufficient rotation. As you can see, basically just kind of rotate our bromines and everything to the right. And then we do end up with an image that if we took it would then superimpose on the original image. Now, what is the difference here? Well, the difference here between this guy, say, and a chiral molecule is it actually does not have 4 different groups attached. So here we see bromine and bromine attached, and that's the same group. So remember, a chiral carbon will have 4 different groups attached to it. This guy's got 2 groups that are actually the same. So what that means is when we do pull out that mirror image, you got kind of 2 groups that are the same. So as you rotate, things tend to fall back into place and they are superimposable. So if you end up with a carbon that has 4 different groups attached, that is what is referred to as a chiral carbon. And if you put that sort of image up to a mirror, it will not superimpose on itself with the mirror image. And if you have basically a carbon that has 2 groups that are at least the same, that will end up being an achiral compound, which if you did sort of cozy that up to a mirror, you would get those guys basically to superimpose. Any questions on that? Here are some everyday examples of chiral and achiral sort of things. We got our gloves, which are chiral, our golf club, which is also chiral. Soccer balls, achiral, definitely, you can rotate it anywhere and it will fit there. Our glass as well, and our shoes here, again, kind of like our hands, are also chiral. So let's take a second here for each of them to determine if these guys are chiral or achiral. So take a moment or two and see what you come up with. Okay, so let's take a look here and see. So really what we want to look at in this case, we get this to actually change, there we go, is, we kind of want to focus in on the center carbon here. And we basically want to look at all the groups that are attached to that carbon. And in this case, there's a chlorine, which is different than a methyl group, different than this sort of ethyl group here, and different than the hydrogen. So that is 1, 2, 3, 4 different groups attached to this. That means that this molecule should be chiral. That also would mean that this guy would be non-superimposable, its mirror image. So the mirror image would be non-superimposable in that case. Any questions on that there? Looking at this carbon, we want to kind of take the same approach. We got a chlorine, which is different than a methyl group, which is different than a hydrogen. But here we now see another hydrogen. So in this case, we have 2 of the same groups that are present. That would mean that we do not have 4 different groups attached, and that would mean that this is going to be a achiral compound. Because of that, that also means that when we kind of cozy this guy up to a mirror, its mirror image should be superimposable. Again, with some rotation, we could get this guy to line up perfectly, again, with the mirror image, or the mirror image can line up perfectly with the original guy. Any questions on that one there? Lastly, looking at this here, we're going to look at our carbon. We see a chlorine, which is different than a methyl, methyl and chlorine different than a bromine. and a chlorine, methyl, and bromine, all different than a hydrogen. So again, in this case, we have 4 different groups attached. That's going to tell us this is going to be chiral. And again, our non-superimposable mirror image. Any questions on any of those 3 there? So understanding chiral carbons, which is sort of what we were doing here, it's really important here in carbohydrates, being able to identify them as either being chiral carbons or achiral carbons. Kind of, as I hit the wrong button there. All right. Now, another way that we sometimes will represent carbohydrates and so forth is with what is sometimes referred to as Fissure projections. They're kind of 2-dimensional representations of a 3-dimensional sort of molecule. We place the most oxidized group up on top, and that's usually something that's got like a carbon oxygen double bond type of thing happening. That usually ends up towards the top. We use vertical lines in place of dashes for bonds that go back. So and we use horizontal lines in place of wedges for bonds that come forward. So sometimes things are represented kind of in 3 dimension as like a little wedge here means it's coming forward or kind of out of the paper. Kind of a dash type of line usually means that it's going back and through the back of the paper and through 3 dimensions. So we sometimes will use some vertical lines and horizontal lines to represent this. So if we take a look at some of these structures here, we have our kind of wedges here, and we also have our dashed lines here, and our more oxidized group up on top, and again our mirror image. And this guy here would have a non-superimposable mirror image, as this would be a chiral carbon right there. That carbon right there that I circled has one group that is different than this entire group, and it's different than that group, and it is different than that group. So that is 4 groups attached to that carbon, which are different, which means that is, again, a chiral carbon that we see there. And a lot of times with carbohydrates, we simply don't write the carbons out. We kind of use almost like line structure, like we did in organic chemistry. So you'll see something, sort of like this, for example. And, there'll be a bunch of maybe OHs and H's. And just like kind of an organic chemistry, every time we have kind of a zigzag type of thing, everywhere there's sort of a point or an end, there's basically a carbon. And the same idea here, everywhere where there's sort of an intersection of lines, it really does represent a carbon. So there would technically be a carbon here where those guys come together, carbon here, carbon here, carbon here. So in this little sort of structure, it actually has a number of carbons that are present. It has 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. So very, very common down here. Again, right here where there's really nothing written and those lines intersect, those are carbons. And again, in this particular compound, there would be 1 carbon, again, 2 carbons in the center there, and 3 total carbons, with our chiral carbon being right there in the center. Any questions on that there? So using this notation, which is very common for carbohydrates, we also have a couple other sort of notations or way that we describe carbohydrates. And one way is by D or L, and find my thing, there it is. So D and L basically means kind of left or right. So D means right. L, which is the easy one, means left. And what are we really sort of talking about? Well, we're talking about basically the OH group on the very last chirocarbon from kind of the top, if you will. So we're looking at the placement of the OH group at the last chirocarbon from the top or the most oxidized group. So again, up here, this guy right here, which is like our aldehyde group that we see in organic chemistry. And we know in organic chemistry, as we talked about, this aldehyde group can be oxidized to a carboxylic acid. So this would be our most oxidized group. When we look at this carbon is attached to one group, two groups, and then pretty much everything underneath is a group. So that's not four different groups. So that is not a chirocarbon. When we look at the carbon that's right here, I'll just put a little circle there. What we see is that is actually a chirocarbon. So let's get rid of some of these lines here and stuff like that. So when we look at the carbon that's now the circle, it has one group, which is this entire thing, which is different than the OH group there, this box, different than the hydrogen, and different than this group down here. That would actually be our very last chirocarbon. You might be wondering, what about the carbon at the very bottom? So if we drew the carbon at the very bottom, which is the CH2OH, and just kind of really drew it out, it has, as you can see, an OH, but it has two hydrogens in addition to what's attached above. But because of these two hydrogens, that makes this carbon actually achiral. So this guy at the bottom is achiral. The carbon right above it, though, is chiral, as it has four different groups attached to it. Now, when we look at this last chirocarbon, which, by the way, is probably, I won't say 100% of the time, but pretty high 90% of the time, it's usually the carbon right above that CH2OH is a lot of times your chirocarbon. Again, not 100% of the time, but a lot of cases it is. When we look at it, we do see that the OH group here is on the left, which is why this gets the L designation for left. Here, when we look at it, our chirocarbon, again, the same carbon, but our OH group on that particular one is on the right, and that is why it gets the D designation here. Any questions on that there? All right, so take a second here and try to decide, indicate whether each pair is a mirror image that cannot be superimposed. So we're actually looking at kind of a double negative there. It cannot be superimposed. So see what you come up with. So let's take a look and see. So really the simple certified approaches are really what it's sort of asking, but the really more simple effect, it's basically asking, if you put a mirror kind of in front of both of these guys, will this guy here be able to be superimposed or not? And really to answer that question, you could kind of really take it very simply by, are we dealing with a chiral molecule or a non-chiral or a chiral molecule? So to determine that, we're going to look at the carbon. And I see one group here, which is different than the methyl group, that is different than the bromine, and that is different than the hydrogen, which means this guy is chiral. And by definition of that, that means that this is a non-superimposable mirror image. So I guess the answer is yes, this contains a mirror image that cannot be superimposed in this question, the way it's asked. Here, same idea, we're going to look at the carbon. We see same, different group, but here, just like we saw earlier, same group that's here. That's going to mean that this guy is going to be achiral. And that means that with sufficient rotation here, we can superimpose this mirror image. So in terms of the question, that would mean no on this guy. It does not contain a mirror image that will not be superimposed. Any questions on that? So kind of the easier way to answer that is to look for whether or not you got a chiral or an achiral sort of compound happening. Any questions on that? So let's talk a little bit more about carbohydrates to get a little bit into these different types of sugars. Carbohydrates, as I mentioned earlier, obviously a major source of energy from our diet. We eat carbohydrates, we go through glycolysis, we use it for energy. We also store some extra in case we need to break it back down a little bit later on and through what's known as gluconeogenesis. It is composed basically of three non-metal elements, are carbons, hydrogens, and oxygens. They're sometimes referred to as saccharides, which means sugar. So they're sometimes referred to as sugars as well. Carbohydrates are produced by photosynthesis in plants, such as glucose, which are synthesized in plants. They make CO2 and water and energy from the sun, and they're oxidized in living cells through respiration. So we get this nice little sort of circle here that's happening on the right, energy from our sun. There it is. Create some photosynthesis. We get some carbohydrates with some oxygen, along with respiration here to use some energy. And again, this nice little cyclic cycle there that keeps it kind of going. There are some different types of carbohydrates that we're going to talk about here in this chapter. So let's talk about the different types of carbohydrates and some of the things that you will need to know about these guys. First off, the simplest type of carbohydrate is one that's referred to as a monosaccharide. Mono meaning one, so basically one sugar molecule, basically there, one carbohydrate basically attached. Disaccharides, di meaning two, basically consist of two monosaccharides put together. And as we'll talk a little bit about, the way we put them together is we take out water. As you take out water, the two sugars basically can then kind of bond together to form a disaccharide. And a polysaccharide is many monosaccharides all put together. Again, they're all put together basically by removing water. And that's what we see down here. Actually, this is breaking them apart. In this case, you can't really break apart a monosaccharide as it's the only thing there. But if you have a disaccharide, if you put the water back in, it breaks apart into two monosaccharide guys. And if you put a lot of waters in everywhere here, it will break it apart into individual monosaccharides. So as we will see, kind of breaking apart disaccharides and polysaccharides, you put water in. To make those guys, you basically take water out and put everybody together. So let's talk a little bit first off, though, about some different types of monosaccharides. So monosaccharides typically will consist of 3 to 6 carbons, and they typically will have a carbonyl group. And if you remember from organic chemistry, it's the same thing. A carbonyl group is our carbon-oxygen double bond. That is a carbonyl carbon, or group, if you want to call it that. And it will basically contain either an aldehyde or ketone, also the exact same thing that we saw when we were talking about organic chemistry. So obviously, hasn't been that long, but hopefully we still remember. This is a aldehyde, right, group. And this is a ketone, that 3 carbon run with our carbonyl group. there in the center. So these carbohydrates or monosaccharides will have one of these groups on top. These are what are considered the most oxidized group, as we were talking about before, and they are put towards the top. Now, just like in organic chemistry, if you remember, this guy always has to be at the end because of the hydrogen. And if you remember from organic chemistry, this guy here is never at the end because of the 3-carbon run that you need. And when we're dealing with carbohydrates, it works the same way. And what I mean by that is, let's just say we had something such as this. Up on top, we would have our aldehyde group. And, you know, again, we would have maybe some OHs happening here, maybe some H's on the rest of them. And just like sort of in organic chemistry, this guy would be the priority in terms of numbering. So where that group is always considered carbon number 1. And again, here where these guys cross would be carbon 2, carbon 3, carbon 4, carbon 5, and this guy down here would be carbon 6. So earlier we were talking about determining D or L. Again, usually from where this guy is located furthest down the road in terms of carbons, which helps us determine that sort of D or L. And again, you can see because of this aldehyde group, it is found towards the end of the molecule, obviously. And just like in organic chemistry, we will have the ketone group not at the end, or the carbonyl part of it. And again, here, if we were to do some numbering, I didn't fill in everything else on here, but this would be carbon 1, and our carbonyl for our ketone would be carbon 2. This would be carbon 3, carbon 4, carbon 5, and carbon 6. And in case you cannot see the ketone part, there's our 1 carbon, 2 carbons, and again, 3 carbon run right there with the OH group. I'm sorry, the carbon and the double bonded oxygen, not the OH group. And again, that is our ketone group, just like we see in organic chemistry. And just like that, we do see the carbon oxygen double bond second in from the end, as opposed to the carbon oxygen bond here with the hydrogen being at the very end. So sort of the 2 functional groups that we commonly see on these monosaccharides is either an aldehyde or a ketone. And depending on which one you have, you may have some different sort of naming or ways of identifying what's going on. So let's take a look at these a little closer. If we do end up with that aldehyde group up there on top, that again is right there. Change colors, I cannot see it. I'm getting old. All right, let's try that. There's our aldehyde group right there. And we call these an aldose. Again, a good way to remember that is like aldehyde. This is an aldose in terms of our carbohydrate. And it's basically because it does have a ketone. It does have an aldehyde group there on top. So this is our aldehyde group up on top. And that is why it's referred to as an aldose. In this case, if we count carbons, this again would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4. So we can also identify our monosaccharide based on how many carbons it has. Triose means it has 3 carbons, tetrose has 4, pentose has 5, and hexose has 6. Those are kind of like our prefixes we've seen before: tetra for 4, penta for 5, hexa for 6. So in this particular case, this would be a tetrose because it has 4 carbons. It would be an aldose because it has an aldehyde group, and that's sort of the basis of the name down here, where it calls an aldotetrose. Aldo again meaning aldehyde, and tetros meaning 4 carbons. You don't have to worry about the actual name here for this particular one, but you do need to be able to identify it as an aldose, and triose, tetros, pentose are hexose. The other question is, how many chiral carbons are there? So take a moment and look at each of the carbons and see if you can determine if there's any chiral carbons present and how many there might be. Remember, in order for it to be chiral, it needs 4 different groups attached. So we just look at this guy. It actually only has 3. 1 group here, 2 here, and pretty much everything below my line is a group. So that's only 3. So that's definitely not 4. Let's take a look at number 2 here. So number 2 has a hydrogen, that's a group, has an OH, that's a group, has this entire thing as a group, which is different than this entire thing. So that is actually 4 different carbons. So carbon number 2 is chiral here. Let's take a look at carbon number 3, and just to kind of clear it up, I'm gonna erase some of these guys here. So we'll do that. We'll get rid of that. Get rid of that. Maybe get rid of that as well. Get rid of that and that. All right. So if we look at carbon number 3 in this case, everything above it would be considered 1 group, which would be different than the OH, and that would obviously be different than the hydrogen, and our group down here, which would be different. That means that carbon number 3 would also be chiral in this case. And lastly, our last choice here would be carbon number 4. And again, we're just going to clean up a little bit here. So carbon number 4, which would be this carbon right here, what we see here again, if we were to draw that out, it would have 2 hydrogens and an OH group. And right there is a problem. That is 2 of the same. That makes it achiral in this case. So what that means is there are actually 2 chiral carbons in this particular guy, number 2 and number 3. Number 4 is achiral. That's important because if we go down from the most oxidated group to the furthest chiral carbon, which is this guy, we will see that the OH group is sitting on the right-hand side. And that would mean that this is a D for right conformation. Any questions on that there? So as this clearly shows, you could absolutely have more than 1 chiral carbon in a carbohydrate, and it does obviously happen. And like I mentioned before, as we again see right above that CH2OH is the last chiral carbon. Again, not 100% of the time, but a good majority of the time. That's where you're going to find it. Now let's take a look at sort of what happens when we got that ketone group involved. And that ketone group works kind of the same way, except that it is referred to as a ketose because it does have that 3 carbon run with the double bond happening. And again, if we sort of highlight it here, there's carbon 1, there's carbon 2, and there's carbon 3 all in a row, along with our OH group. And that is basically our ketone group. So much like the aldehyde group is called an aldose, if you got the ketone group happening here, this is what is referred to as a ketose. If we count up the carbons, this is again going to be carbon 1, that would be carbon 2, that would be carbon 3, carbon 4, carbon 5, and carbon 6, which means in this particular case, this would also be known as a hexose because it contains 6 carbons. And in this particular case, we would have a chiral carbon right there. Again, everything above it is different than the hydrogen, the OH, and everything below it is different. Number 4 would also be chiral. To the left hydrogen, to the right OH, everything above is different than what's below. Number 5 here would also be chiral as well. Again, 4 different groups attached. Hydrogen, OH, everything above the carbon all the way to the top, everything below the carbon. Carbon number 6 would be achiral again because of the 2 hydrogen. That again means if we go the furthest down in terms of chiral carbon, we again see that the OH group is on the right. which means this would be D. This is fructose, which is a ketohexose. This is one you should probably star. You should be familiar with the structure of fructose. So you should be familiar with the structure here of fructose, the 6-carbon ketone type structure. Any questions on that particular one there? So again, maybe not to draw, but if you see the structure, you do need to kind of be able to recognize it as fructose. All right, let's take a look at an example here. Maybe if it comes, there it is. So in each of these, decide if this is an aldose or a ketose, and is it tetrose, pentose, or hexose? So take a moment or two to see what you come up with. Okay, let's take a look. So starting here, really to determine aldo or keto, we're looking really for the functional group, just like in organic chemistry. So we're looking for either the aldehyde group or really a ketone group here. So on the first one here, we could clearly see the aldehyde group there. That tells us it's an aldose or an aldo. And basically to figure out the tetrose, pentose, or hexose, we just need to count the carbons. So that's 1, that's 2, that is 3, that is 4, that is 5, and that is a 6 right there, which would be based off of like hexa. So that would be a hexose for 6 carbons. Any questions on that? Looking over here, again, you can hopefully recognize the ketone group coming right through here. So there we see our ketone group, which would tell us it's a ketose. And because it's a ketose, we also want to see out how many carbons. So 1, 2, 3, 4, and 5 carbons in this case. 5 is based off of like penta, which would be a pentose. Any questions on either one of those there? So let's talk a little bit about the structures here of our monosaccharides. Now, like I said before, we can use some Fissure projections where we do place the most oxidized group up on top. And as we've been doing again, we use a lot of times no carbons. We just use those cross lines where we do see those chiral carbons as intersections as it comes through here. And again, as you can see, last chiral carbon, as we saw earlier, right there, and that is a left or an L. And same thing here, last chiral carbon right above there, and that is on the right hand side, which would be our D projection. So looking at some examples of D and L monosaccharides, here are a few that pretty much this page as well. You should put a little asterisk, same deal. You need to be able to recognize the structure of glucose, ribose, and galactose. Again, not necessarily being asked to draw it, but if you see the structure, be able to recognize it as one of these 3 guys. Let's take a look at each of these to sort of see what we're dealing with. First off, for glucose, we do see the aldehyde group, which tells us as an aldose. We also see 1, 2, 3, 4, 5, and 6 carbons, which tells us it's a hexose. And this is D-glucose because the last chiral carbon right there on the right-hand side. This is ribose, which also is an aldose, as we see the aldehyde group there on top. In this case, it's 1, 2, 3, 4, 5 carbons, which tells us it's a pentose. And again, the last chiral carbon right there, and our OH group again on the right-hand side, hence the D. And lastly, this is galactose, also an aldose. Also has got 1, 2, 3, 4, 5, and 6 carbons, which is a hexose. And it is, pretty similar to glucose. A couple of differences on there where the placement of the OHs are, but has, a similar type of structure. This being L as the last OH group in the carbon, chiral carbon there is on the left. So that is L-glucose. Any questions on that there? All right, so let's take a look at these here, decide if each of these are D or L, and also decide is an aldose or a ketose. So take a second and decide. Ketose question, we see the aldehyde group, so this is an aldose. By the way, there is 1, 2, 3, 4, 5 carbons, which is a pentose, as we talked about. There are actually 3 chirocarbons in this particular compound. That is a chirocarbon right there. That is, and that is. And to determine D or L, we want to go the last chirocarbon for our most oxidized group, which should be the carbon-oxygen double bond. And that would take us all the way down to this guy. And we see that it is on the left. So this should be L-ribose in this case. Questions on that one there? Here again, we see the aldehyde group, which tells us it's an aldose. It's got 1, 2, 3, and only 4 carbons. This would be a tetrose, as it has 4 carbons. Again, here where it's crossing, that is a chirocarbon. That is a chirocarbon. The furthest one down the road here from our carbon also finds our OH group there on the left, which gives us an L in this case for that. And lastly, this is a carbon, 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 which is 3 carbons in a row. And that is our ketone group. And that means that this is a ketose. It has 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons, which is our fructose and our hexose. It has a chirocarbon located at each of these following spots. 1 right there, 1 right there, and 1 right there. Again, looking at the furthest OH from our carbon-oxygen double bond, which is right there, we see in this particular case, it is on the right-hand side, and that would give us, not R, sorry, give us D, fructose in this particular case. Any questions on any of those there? Okay, so let's take a look at a couple of these sort of monosaccharides a little bit closer. Let's take a look at D-glucose. D-glucose is found in fruits, corn syrup, and honey. Again, the structure over there, as we talked about earlier, you should be able to identify it. It has a molecular formula C6H12O6. It's known as blood sugar in the body. It is basically the monosaccharide of polymers of starch, cellulose, and glycogen, as we'll talk about. Again, as I mentioned before, body uses it for energy through glycolysis. Again, stores some of it. You need to kind of break it back apart a little bit later on. As we saw earlier, it is a 6-carbon structure, hexose. It has the aldose and obviously D-glucose, meaning that our final OH group on the chirocarbon is there on the right-hand side. In the body, glucose has a normal blood level of about 70 to 90 milligrams per deciliter. You can do a glucose tolerance test where it measures basically your body's sort of blood glucose for several hours after you ingest some of it. And a couple of things could happen. You may find yourself being hyperglycemic, hyper meaning more than, as you can see here, your little scale here is a little bit more than normal in terms of your blood glucose levels. Or you can find yourself being hypo, like we talked about, hypotonic, could be less than. And again, you see a little bit less of a blood glucose level in that case. Obviously, one or the other there, both can have some bad effects on you depending on your blood glucose levels. Obviously, since we use it for energy and so forth, you don't have the right amount, you do suffer some side effects of that, obviously. D-fructose, we saw earlier, also, as you can see, has pretty much the exact same molecular formula as glucose, the C6H12O6. Again, though, it is different than glucose, the major difference is it has that ketone group, or the keto group right there. This being D-glucose, as that is our last chiral carbon, where our OH group is on the right. It is the sweetest carbohydrates. It's found in fruit, juice, and honey. And in the body, it can convert into glucose in the body. So it can do that conversion. Again, this is another structure like we talked about earlier that you do need to be familiar with. Galactose as well is another one that again shares the same molecular formula. It's not found free in nature. It's obtained through basically the disaccharide, which is known as lactose. It has a very similar structure to glucose, except that carbon number 4 there in the location of the OH group. So remember, up here is carbon 1, that's carbon 2, carbon 3, and carbon 4. So this is a major difference between that and glucose. And if we take a look at glucose, which we just had up here, and we can see a carbon number 4 for glucose, we got the OH group over here. So again, a difference between these two found right there. The rest of the structure very, very similar to each other, just sort of that difference at carbon number 4. Draw the Fissure projection of glucose. Again, you won't be asked to, fructose, you won't be asked to draw it, but you do need to be able to recognize it. So again, looking at the structure, this is what it looks like. And again, we have our keto group. Sometimes it's sort of the structure there. They will kind of draw it like this. It'll kind of look like this. And again, just a sort of straight line. There is obviously a carbon there. And obviously there's our first carbon, our second carbon. Obviously that would be our third carbon. So you'll sometimes see it, kind of drawn almost like this. And you don't want to overlook that there is a carbon here. So sometimes people will overlook that part of it. Again, it has 1, 2, 3 chiral carbons happening here. Again, that guy is achiral. And so is this guy up here. He's achiral as well, because he has the 2 hydrogens that are present. Any questions on that there? Okay, so these monosaccharides can basically fold in on each other, or on itself, I guess is a better way of saying that. It can fold in on itself and basically create a cyclic structure, basically a ring structure. And there's basically 2 types of cyclic structures that we come across, and it sort of depends, how it comes together as to, which one you get. And they're both kind of based off of what we saw in organic chemistry, sort of a hexane ring and a pentane ring, except that our cyclohexane and cyclopentane, except that there's one less carbon. there's actually oxygen inserted into the ring. So this is actually like a 5-carbon ring. This is a 4-carbon ring, and it's kind of similar to, again, cyclohexane. 5 carbons being 1 carbon there, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. Over here, 1 carbon, 2 carbons, 3 carbons, and 4 carbons. So how do we figure out sort of, which one we're going to get? There's sort of a pattern or how you want to approach this. So let's just take a random sugar here. And I'll just draw it kind of like this. Let's see, what do I want to do? Let's go 2, 3, 4, 5. We'll do this. And just randomly placing these guys here. We'll put that there. We'll do this guy here. We'll do that there. Let's do this and this and that and that. Now, if we want to basically turn this guy into a cyclic structure, so we basically want to take this guy and allow it basically to close up on each other. What's going to happen in this particular case is it is always going to kind of be the last chiral carbon that's going to find the most oxidized group. So let's number our carbons here. So let's do a little numbering here. So this is carbon 1, that is carbon 2, that is carbon 3, that is carbon 4, that is carbon 5, and that is carbon 6. So in the case where you have basically 6 carbons, the last chiral carbon, which is right here at carbon number 5, will then go and find the carbon-oxygen double bond, which in this case is carbon number 1. And that is going to make up the ring that you're going to get. So how do I know how many carbons are in there? You basically could count how many carbons. So that is a carbon, that's 1, that's 2, that's 3, that's 4, that is 5. So when this thing closes up, it should make a 5-member ring, and that's how we know which ring we should draw. So once you determine that, you basically can draw the ring. So there we're going to get our oxygen incorporated inside the ring. And that oxygen gets incorporated, from the oxygen up here, carbon 1 and sort of carbon 5. One of those oxygens sort of finds itself in the ring. Now, a couple of things. The first thing that we see is here at carbon number 6, that CH2OH group is not part of the ring structure, right? We can see it's outside the little arrow. And that group will always end up to the left of the oxygen and above the ring. So I'll just draw it out of the writing here, CH2OH. So that will always end up above the ring to the left of the oxygen on that carbon. What we could do with that is that's a really good piece of information, because we could see from our original structure that is carbon number 6, right? We can see that as carbon 6. And now we could actually number the ring going counterclockwise, coming down. This would be carbon number 5. This would be carbon number 4. This would be carbon number 3. This would be carbon number 2 and carbon number 1. So this carbon 6 is outside of the ring. We number counterclockwise the rest of the carbons. And that's really important, because now we are pretty close to determining sort of what we want in this picture. The next thing that you could do is basically we're going to take this structure and we're basically just going to drop it on its side. So we're going to drop it to the right on its side. And if we do that, I'm just going to redraw it. So all I'm doing is dropping the structure down to the right. This then would be This would be carbon 1, this would be carbon 2, this would be carbon 3, carbon 4, carbon 5, and carbon 6. Now, obviously, when I drop it to its side on the right-hand side, everything that is on the right-hand side ends up down. What I mean by that is this guy has the H that would be there. This would be the OH. This would be the H. This would be our OH here. Let's see here. I think I missed that right there. I counted wrong. Sorry there. Try again. All right. Starting at carbon number 2, which is right here, the OH should be here. There you go. That's better. That would be the H. That would be the OH, and that would be the OH. And obviously, everything to the left of my structure will end up up. We'll actually end up here, and that would be our hydrogen. That would be our OH. That would be our hydrogen and our hydrogen. So essentially, all we did is take the structure, drop it on its side. Anybody that's pretty much on the right-hand side will end up down. Anybody that's on the left-hand side will end up when you do that. And now we're really ready to complete our picture. First off, the connection that occurs here when we form the ring is carbon number 5 and carbon number 1. Again, an oxygen gets incorporated into here. So when we come down here, we actually skip number 5 and we go to number 4. And when we look at number 4, we see the OH group is down, which means we draw the OH group down. When we go to carbon number 3, we see the OH group is up. So at carbon number 3, we draw the OH group up. At carbon number 2, the OH group is down, which means at carbon number 2, we draw the OH group down. Any questions on that? Now, for simplicity's sake, most of the time people will draw those lines like that. What is on the other side is actually a hydrogen, but a lot of times people won't draw it just so it doesn't get so cluttered. But that is what's on the other side of sort of the line there. It's a hydrogen. But again, a lot of times people won't draw it so not so crowded and stuff like that in the picture. Now, you may be wondering what happens at number 1. And because that sort of is where we join the ring together, it will actually tell you how you should draw sort of number 1. And basically there's 2 options. There is the alpha anomer, which means the last OH group goes down. And there is the beta anomer, and that means the last OH group goes up. So it'll ask you to draw 1. So if I did this guy and put that very last OH group down, this would be our alpha because that OH group is down. I could redraw the exact same guy here. Again, down, up, down, and if I go up on this one, that would be our beta. So they will give you sort of direction as to which one you should draw, either the alpha or the beta. And again, that's how you can determine how to finish it out. Question on that there? Okay. Let's see what we got here. Actually, so why don't you try one real quick? Why don't you draw this guy into a ring structure? So let's do this. And why don't you draw the, let's do Why don't you draw the beta anomer of this guy? All right, so turn this guy into a ring type structure and see what you come up with, and we'll take a look at it here in just a second. First off here, we maybe want to count up how many we got going on here. So we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. In this case, always that 5th chiral carbon here when we got 6. Going to find our carbon oxygen double bond. And that means that we now can figure out the proper ring to draw by just really counting up the carbons involved in that situation. So that's 1, 2, 3, 4, and 5 carbons. So remember, the 5 carbon ring pretty much looks like cyclohexane, except that there is an oxygen that gets put in there. By the way, it's that oxygen right there that gets put right there. Now, when we do that, just like we saw before, our carbon number 6 guy is not part of the ring, so he does end up above the ring to the left there of our oxygen. And that is carbon 6, which allows us to now number our ring counterclockwise. And if I could count, that would be good. 4, 3, 2, and 1 in this case. We're basically going to take this guy and drop it on its side. And again, when we do that, basically everybody on the right-hand side goes down. Everybody on the left-hand side goes up. Again, if you just took it and dropped it on its side. So I'm not going to redraw it in this case. I'm just going to remember that. I'm going to skip 5 because that's where the whole ring kind of comes together up here in this top part. We're going to go to number 4. And number 4, we see the OH group is on the right, which means it should end up down. We're going to go to carbon number 3, which we also see the OH groups on the right. So when we drop it, it should also come down. Number 2, we actually see the OH group is on the left. So when we drop it, it actually ends up. And now my last one here, which is carbon number 1, is determined by the beta here. And that means that the last OH group there should go up for our beta anomer. Question on that drawing there. So as we've been talking about, we do form these sort of ring structures. They actually form what are referred to as cyclic hemiacetals. Remember, those hemiacetals are when we have basically a carbon that has an OH group attached and an oxygen carbon group and a hydrogen attached. The OH are part of the same molecule for hexoses. So when you got 6 carbons like we looked at already, it's usually carbon number 5 that will go and find, again, the carbon oxygen double bond. So it could be the aldehyde group at the top. It could be the ketone group a little bit in, and it will form a structure based on either really 5 carbons or 4 carbons that does have that OH group that's basically attached in there. So again, if we look at this guy, which is oddly, I think the one we just did actually. Again, what you want to do is drop it on its side. If you like to redraw it, again, we're going to get this carbon coming over here to attach. And again, it's actually this oxygen that gets incorporated in there. And this hydrogen actually comes over here to this oxygen in that process. That gives us our group that's outside of the ring, allowing us to, again, number backwards here, counterclockwise. And then we, again, do skip our carbon number 5, as that's where the ring came together. And we go to carbon 4 and work our way around. And again, either our alpha or our beta will be asked of us. And again, if it's the alpha, that last OH group will go down. And if it's beta, the last OH group there will go up in this case. Any questions on that one there? All right, so why don't we try another one here, maybe a slightly different one. So why don't you draw this guy into a cyclic structure? Let's go with this. Let's do that. All right, and why don't we do, since we just did beta, why don't we do the alpha anomer? So why don't you draw the alpha anomer of this guy? So turn it into a ring structure and see what you come up with. And then we'll take a look at it. Okay, so let's take a look. So we actually do want to kind of approach it the sort of same way. So we can start by counting carbons here. And if we count carbons again, towards the top there where our oxidized group is 1, 2, 3, 4, 5, and 6. Again, you could probably recognize this obviously as a ketose. So this is the ketone group. Same thing going to happen here. It's actually going to be carbon number 5, which is our last chiral carbon, and it's going to go up. And again, in this particular case, it is not going to go to carbon number 1 because it is interested in the carbon oxygen double bond. So it's actually going to go to carbon number 2 in this case. So it's always going to kind of go to that carbon oxygen double bond. And in the case of the ketone, it will probably be carbon number 2 rather than number 1 like we see in the aldehyde. What does that mean in terms of the ring structure we should draw? Well, there's 1 carbon there, there's 2, there's 3, and there's actually only 4 carbons involved in this ring. That means we actually should draw the 4 carbon ring, which looks something like this. Now, in this particular case, we do have 1 group up here that's not part of the ring, and we have our traditional carbon number 6 that is not part of the ring as well. Just like traditionally here to the left of that oxygen above the ring is where carbon number 6 will go. That then means that this is carbon number 5 in this ring. This is carbon 4. That's carbon 3. That is carbon 2. And carbon number 1, which is right here, as we can see, is off of the ring. So it's actually not attached to the ring here. Any questions on that there? We're going to do our same deal when we would take this guy basically and drop him on its side. Just like before, everybody on the right will go down. Everybody on the left will go up. So we will skip number 5 like normal, which means when we go to carbon number 4, we see the OH group is on the left-hand side, which means it will end up. When we go to carbon number 3, we see the OH group also on the left, which means it will go up. Now, carbon number 2 and carbon number 5 is where that whole ring came together, which again, this being the oxygen that ends up in the ring, by the way. So what do I do with this? Well, that is going to be based off of what we're asked to draw here, which is the alpha. That means that the OH group should go down there. And on the other end of that OH group is actually going to be our carbon number 1, which is off of the ring. Obviously, if it was beta, it would be flipped. The OH would go on top and the CH2OH would go on the bottom. Any questions on that one there? Questions on how to turn these guys into ring structures? Okay. Now, what happens if we kind of wanted to go backwards, like from the ring structure to like the straight chain, if you will? Well, let's see how we could maybe figure out how to do that. Let's do our CH2OH. Let's Do a little of that action there. And let's just do OH, OH, and let's do OH. And why not? We'll go OH down here. Okay, so let's say we wanted to take this guy back to sort of this straight chain, right? So we want to go back now, and maybe we want to do L or D. Why don't we just choose, let's choose D for why not? So let's say we want to draw the D of this guy in the straight sort of form. So first off, if we look at our ring, we see that, you know, if we count up the carbons in our ring, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So remember that a 5-member ring here is going to get us, with 1 more carbon up on top, that is 6. That is going to give us basically 6 carbons. And we know that this carbon is carbon number 6. That is carbon 5. That is carbon 4. That is carbon, bad math there. That is carbon 3. That is carbon 2. And that is carbon 1. So if this is carbon 6, this would be carbon 5. That would be carbon 4. That would be carbon 3. That would be carbon 2. And that would be carbon 1. Now, I know that this is going to probably be an aldehyde group up on top. The reason I know that is, as we just saw in the last one, when we had a ketone, we had a group on both sides, right? So we had that kind of CH2 group on both sides, like we had on here. And that was a result of really this being a ketone. Here we don't see that, so it's probably safe to assume that it's going to be an aldehyde group up on top. So what is left? Well, what is left is we just need to recreate it. What we talked about was, if you have this guy and you throw it on its side, everybody that ends up down is on the right-hand side originally, right? Everybody that's on the upside is on the left-hand side. So working our way backwards, again, we're going to skip 5 for now. So we go to number 4. Number 4, we see the OH is down, which means that OH group should be on the right-hand side, right? So when we flip it on its side, it ends up down. Carbon number 3, we see the OH group is up, which means it should be on the left-hand side, like we see. And carbon number 2, we see the OH group is up, which means it should be at carbon number 2 on the left-hand side. Hydrogens would be on the other sides here. Now, our last chiral carbon is actually determined by this, which is D, and D means right, which means on number 5 here, I should put my OH group there on the right for my D. And now I have now gone backwards and opened up the ring into the straight chain. Question on that there. So why don't you take a minute or so here, and why don't you give it a try. Let's do. And let's do this. Let's do this. Let's do this. Let's do this. And why don't you draw the L? So open that thing up and draw the L version of it. Take a minute or two, then we'll talk about it. All right, so since we're kind of getting to the end, let's take a look again. Just counting up carbons. That's a carbon 2, 3, 4, 5, and 6 here. Again, I do not see a carbon hanging off of this side, so no carbon, right? So I know it's probably going to be an aldehyde group. I also know I need 6 carbons to do that. So that is 1. And then that would be 2, 3, 4, 5. And we know that carbon number 6 there is going to be on the bottom, which is this guy. Allows us to number counterclockwise. And again, this would be obviously carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Skip a number 5 like normal. We go to number 4. We see that it is up, which means it should be on the left-hand side there, carbon number 4. We see again at carbon number 3, it is up, so also should be on the left-hand side. We see carbon number 2, it's down, which means it should end up on the right-hand side. Again, hydrogen's on the opposite sides here. And our last here is going to be determined by the L, which means left, which means our last OH group there will go on our left-hand side. Any questions on how to kind of go backwards here from the ring to the straight chain? Okay, so we will lay it up there today. And I think what's going to happen is this. We will finish up chapter 13 here on Wednesday. And I think what I'm going to do is I'm going to post up a recording of the things that you need to know from chapter, I guess it'll be 15 and 16. Again, there's not the entire chapters, but the things that you need to know. So I'll post that up tonight, so you have plenty of time, a week and a half to watch it. It'll probably only be maybe an hour for both chapters together, I think. So you'll get that done, and we'll wrap up the rest of this carbohydrates on Wednesday. And during discussion today, we will wrap up the nitrogen guys, and then those have discussion obviously on Wednesday. We'll do that for you as well. Your exams will be posted a little bit later tonight. And lastly, a reminder that the final exam should be 1 week from Wednesday, and it does start earlier at 4:45. So again, make sure you adjust your schedule accordingly so that you can log in and obviously take the final when it is scheduled. All right.